In this video, let's set the foundation for the topic of random walk that we're going to discuss in the upcoming videos. And a random walk has something to do with an AR process, an autoregressive time series. And namely, that's going to be the time series that's not going to be stationary. So in this video, we're going to see what is the requirement for an AR1 process, the most simple autoregressive model, to be stationary. And the random walk that we're going to have a look at is going to be the time series that's not going to respect that criteria. So suppose we have this AR1 process where we regress sales in the current period on sales in the previous period, and our beta is that slope coefficient that's showing the correlation between the current period of sales and the previous period of sales. And as always, we have this error term. Now, under stationary conditions, we know that the error term is gonna be identically and independently distributed with a mean of 0 and a constant variance, because that's what stationarity of variance means. The variance is going to be constant around a certain value, and we're going to use this mathematical property of variances as well to prove a point. Now let's use the property of stationarity of variance to find out the criteria for beta. What kind of beta do we want to have a stationary AR process? So let's take the variance of each side. We're going to take the variance of sales at a certain point in time, which means we're taking the variance of this entire expression, because if we do it on the left side, and this is an equation, we must do it on the right side as well. So we're going to take variance of that entire thing. Let's just copy paste it so we can do it faster like that. Copy paste it below. Now let's solve and see what we get over here. Close the brackets. What's going to be the variance of sales at that specific point? Well, that's going to be the variance of beta times sales in the previous period. Now let's use our mathematical property that we just discussed, this one over here. We're having here beta, which stays for a constant like a, and we're having a term which stays for the variable of x, pretty much the same thing. So we're gonna have that constant to the power of 2, which is gonna be a squared times the variance of that variable. So we're going to have variance of sales at t minus 1 plus the variance of the error term. So we're going to write the variance of the error term as well. Variance of the error term. Now let's see what we have over here. The variance of the error term under stationarity conditions, which we're working with right now, has the constant variance of sigma square. That's going to take the value of sigma square, and over here, I'm sorry, I wrote a square, should be beta square. That takes the value of beta. Beta squared times the variance of st minus 1. Now one thing we know about stationarity of variance is that under stationary processes, under stationary time series, the variance at one time is equal to the variance at the future value. So the variance of sales at a certain point in time is equal to the variance of sales in the previous time period. Now with that in mind, we can substitute the value of the variance of sales in the previous period with the variance of the sales in the current period. So that's going to take the value of v, the variance of st, and we're keeping variance of st on the left side as well, variance of st over here. Now let's take the same terms on one side. So let's take everything with the variance of st on one side, meaning we're going to take this entire expression to the left over here, and we're going to have vst minus beta, let me copy paste it as well, minus beta square times variance of st, so we copy and paste it here below, equals to sigma square. So we write equals to sigma square, equals to sigma square. Now what's a common factor here? Variance of st. We can take the variance of st as a common factor, and in brackets we're left with 1 minus beta square, right? That's the remaining terms. Here we have 1 left, so 1 minus beta square from the next term is equal to sigma square, so that's equal to sigma square over here. Now we're interested in the variance of sales at a certain point in time. Let's divide both sides by 1 minus beta square. So the variance of st, is going to be equal to sigma square divided by 1 minus beta square, sigma square divided by 1 minus beta square. Now what do we know about variances? What properties do we know? The variances is the sum of residuals to the power of 2, sum of squared residuals. So that can only be positive because we're dealing with squares, with squared values. Now over here we have sigma square. Well, by definition that's a squared number, so it's positive as well. The only way to make this entire expression positive is to make 1 minus beta square positive. 1 minus beta square must be positive. Now one criteria that must happen is that 1 minus beta square cannot be equal to 0. 1 minus beta square cannot be equal to 0 because division by 0 is undefined. So beta square cannot be equal to 1. Beta square cannot be 1, meaning that beta cannot be equal to 1. Beta cannot be equal to plus minus 1 actually. Plus minus 1. So that's a property. That's going to be a property of the AR process to be stationary. Beta cannot be plus minus 1. But how should be beta? Well, beta square cannot be greater than 1, right? Because if it's greater than 1, let's say 2, 1 minus 2 is equal to minus 1. That's a negative value. Negative with a positive will make the variance negative, which is not possible. So beta square must be less than 1. Beta square must be less than 1. If we take it in absolute value, then beta must be if you take square root of both sides, then beta in absolute value must be less than 1. Beta in absolute value must be less than 1. And what is that? That is the criteria we're interested in. This is the criteria for an autoregressive time series to be stationary. And we're going to see in the upcoming videos that the random walk is going to be the autoregressive time series, which does not satisfy this condition.